Hello and welcome to today's lesson looking at the conservation of momentum, which forms part of the forces topic in GCSE separate science physics. So in today's lesson, what we're going to be looking at is we're going to be looking at how to apply the conservation of momentum to different situations. So if we're successful and we learn in today's lesson, we should be able to A, calculate the momentum for an object, understand how momentum can be conserved for a system, and then manipulate the conservation of momentum to calculate values in a system. So this part of the lesson is going to be on this part of the specification, which is 4.5.7.2, the conservation of momentum. And you'll note here at the bottom where it says students should be able to complete calculations involving an event such as a collision of two objects that is separate science only content. So it's not covered on combined science. Now, in collisions and explosions, the total momentum is conserved. This means the total momentum of a system before is the same as the total momentum of the system afterwards, which is derived from Newton's laws of motion. So what this means is the total momentum before, so the momentum of object 1 plus the momentum of object 2 must equal the total momentum of the objects afterwards, so the momentum of object 1 plus the momentum of object 2. Now the individual objects can change their momentum in an event, but the overall momentum of the system must stay constant. So for example, say before the collision, object 1 has a momentum of 2 kg meters per second, and object 2 has a momentum of 0 kg meters per second. So it will give us a total momentum of the system before the collision of 2 kg meters per second. But let's say after the collision, object 1 now has 1 kg meters per second, and so does object 2. So the total momentum is 2 kg meters per second. So whilst the total momentum of the system has stayed constant, it was 2 before, so it's 2 after, the individual objects in the system have changed their individual momentum. So that's a very important idea to understand regarding this law in physics. Now, for an individual object to change its momentum, a resultant force must be placed on the object. So we can tell in this example, object 1 and object 2 have had a resultant force placed upon them. Why do we know that? Because their momentum has changed. Now, it's very important to note that we can actually work out momentum with the equation mass times velocity. So we can actually expand out that previous equation of momentum 1 plus momentum 2 before equals momentum 1 plus momentum 2 after by saying mass of 1 times velocity of 1 plus mass of 2 times velocity of 2 must equal mass of 1 times velocity of 1 plus mass of 2 times velocity of 2. So we'll just expand it out to include the entire equation for momentum. Now, in an examination question, you'll be given all of the values in the system except 1, and you'd then be asked to work out the missing value. So that will involve a rearrangement of this particular equation. So one of the most fundamental laws of physics is the conservation of momentum. It's based on Newton's third law of motion. Now, in any collision or explosion, if there is no external force applied to the system, the total momentum of the entire system is the same as the total momentum after the collision. Now, we can use this effect to calculate properties of an object, because we can say total momentum before equals total momentum after. So the mass before times the velocity before equals the mass after times the velocity afterwards. Now we need to consider the total momentum of a system in a collision. Now for a system of objects, like we said before, the total momentum of the system before equals the total momentum of the system after, as long as there's no external forces on the system. So this can be observed in a collision where objects hit each other and move away from each other. So we can say momentum before equals momentum after if we consider there are no external forces on the system. Now another way of saying this is to say that the system is a closed system. Now, we can therefore say in this example, because the object A is going to collide with object B, and object A and B afterwards are going to stick together and move away from each other, that the momentum of A plus the momentum of B beforehand must equal the momentum of AB afterwards. Now we can consider this for a system which has at least one dynamic object before contact, and this is what we call a collision. So let's look at the following example. So you are given the mass of object 1, it is 2 kilograms. You're given its velocity, it's 5 meters per second. Now it hits object 2, which has a mass of 4 kilograms but has a velocity of 0 meters per second. They then stick together and move away from each other. So what is the velocity of the two balls stuck together after the collision? Well, this is how you answer any of these types of questions. Step 1, work out the side of the collision that you've got enough values to work out the momentum for. So in this example, we've been given enough information to work out the total momentum before the collision. So we say 2 times by 5 plus 4 times by 0, so that's 10 plus 0, so the total momentum before is 10 kilograms per meter seconds. Now, this allows us to then move on to step 2, which is that momentum before is equal to momentum afterwards. So if the momentum before was 10 kilograms meters per second, that tells us the momentum afterwards is 10 kilogram meters per second. So therefore that's our second step. Now the third step is then to use the equation momentum equals mass times velocity to then rearrange it to work out the term we want to. Now in this question we want to work out the velocity. So we rearrange the equation to say velocity equals momentum over mass. Now we know the momentum is 10 from step 2. Now we know what the mass is because we have the masses of them originally and they're stuck together. So if a 2 kilogram ball sticks to a 4 kilogram ball, the overall mass is going to be 6 kilograms. So the sum we're going to do is momentum divided by mass. So 10 divided by 6, so it's 1.7 meters per second. Now, we've just got to take a look at that answer after we've calculated it. So we carry out a logic check. Does the answer look sensible? Now, let's think about it. If momentum is being conserved, the mass moving afterwards is larger because only 2 kilograms is moving before the collision, but after the collision, 6 kilograms is moving. So therefore, the object should be moving slower than before the collision because mass times velocity is momentum, and if momentum is constant, if mass is going up, velocity is going down, and that's what's happening because it starts with the velocity of 5 meters per second, and after the collision, the greater mass is now moving 1.7 meters per second, so it makes sense. Now, another example, another event where momentum is conserved is in an explosion. Now, in any explosion, the total momentum of the system is 0. So an explosion, which is motion where objects originally start at rest and then move away from each other, conserves momentum. So beforehand, the object is not moving. So the total momentum of the system is 0. So for momentum to be conserved, the total momentum of the system throughout must be 0. So it means after the explosion, the total momentum must be 0. But after the explosion, both objects have a non-zero momentum. The two fragments produced on the original are now moving, so have momentum. So how can we have a total momentum of 0? Well, let's think about how this could take place. So the overall total momentum of the system after the explosion must be 0 to conserve momentum. This occurs as the individual momentums of the fragments are in opposite directions. So they've got opposite signs. So one momentum is a positive and the other momentum is a negative. Now, if it's not given to you in the question, you can decide which is the positive and which is the negative. Now, this occurs as the two fragments are moving in opposite directions. So this gives them opposite signs like we talked about before with vectors. Now, this can work out and give you a 0 value because, say, for example, one is plus 20 kilogram meters per second, the other will be minus 20 kilogram meters per second, which gives us an overall momentum of 0 kilogram meters per second. So in an explosion, when two objects A and B explode when they start at rest, momentum has to be conserved. So the momentum before is equal to 0 because nothing is moving. Now momentum afterwards is the momentum of A plus the momentum of B. So if momentum before equals momentum after, 0 equals the momentum of A plus the momentum of B. So therefore momentum of A equals minus momentum of B, which makes sense as A and B will be moving in opposite directions. One will be going one way and the other will be going the other way. So if we expand that out, we can say mass of A times by velocity of A equals minus mass of B times by velocity of B. But obviously this is only true when both objects start at rest and then move away from each other after the explosion. Now, let's look at an example question. So, you've got a bomb or an explosive which has a mass of 10 kilograms and a velocity of 0 meters per second before the explosion. Afterwards, the bomb breaks into two fragments. Fragment 1 has a mass of 3 kilograms, but we don't know its velocity, whilst fragment 2 has a mass of 7 kilograms and it's got a velocity of 2 meters per second. Note that defined in this question, move it to the right as positive. So what's the velocity of bomb fragment 1? Well, to do this, we've got to take another 3 steps like I mentioned previously. Step 1. Work out the momentum for the fragment in the explosion, which you can do. Now, we don't have enough information to work out fragment 1, but we do have enough to work out fragment 2. So we do momentum equals mass times velocity, so it's going to be 2 times by 7, so we get 14 kilogram meters per second. Now we know that for step 2, if the total momentum before is 0, the total momentum afterwards is 0, so the momentum of 1 plus 2 is equal to 0, so we know the momentum of fragment 2 is plus 14, so therefore the fragment 1's momentum must have a momentum of minus 14, because plus 14 minus 14 equals 0. So with step 2, we've worked out the momentum of fragment 1, and then we use the equation momentum equals mass times velocity and rearrange it to work out either m or v depending on the question. So velocity, v, is equal to momentum over mass. We know the momentum is minus 14 and the mass is 3 kilograms. So it's minus 14 divided by 3, so we get minus 4.7 meters per second. Now the minus means it's moving in the opposite direction to fragment 2, which is indicated in the question. Now once again, we carry out a logic check. If fragment 1 and fragment 2 have to have the same momentum but in opposite directions for the law of conservation of momentum to be correct, therefore they've got to have the same momentum. So this means the heavier fragment should be traveling slower because momentum is mass times velocity. So because fragment 2 has the higher mass, it should have the smaller velocity. And that makes sense because it does from our answer that we calculated. It's always really important you check your answer after you've worked it out to make sure it looks correct. It follows the logic. Now, we can look at this idea, the conservation of momentum, by looking at an example of an explosion in the real world. So look at the example of firing a gun. So when you fire a gun, the gun or the explosive will always recoil and move backwards. So this happens for lots and lots of objects, for guns, cannons, any type of artillery. It's called what we call the recoil. Now, the recoil in any explosion can be explained by the conservation of momentum. So let's consider a gun and the bullet. So the total momentum before, because the gun and the bullet are not moving before the explosion, must be 0. So the total momentum before the explosion is 0, so the total momentum after the explosion must be 0. So currently our system has no total momentum, so it must be conserved. So after the gun has been fired, the bullet moves off and has a momentum, and so does the gun. The gun moves in the opposite direction because they'll both have their individual momentums which will cancel through to give us a total momentum afterwards of 0. So the movements are in opposite directions. The gun recoils in the opposite direction to the bullet, so the gun will have a momentum and the bullet will have a momentum. Each momentum is in the opposite direction. One is a plus, one is a minus, so they'll cancel through to give a total momentum of 0. Now, interestingly, if you look at the bullet, now we know that momentum equals mass times by velocity, and if the momentum of the bullet and the momentum of the gun have to cancel out to equal 0, because the bullet has a lower mass than the gun, it must have a higher velocity than the gun. So whilst the gun has a higher mass than the bullet, it will have a lower recoil velocity than the bullet being fired has its velocity to get the momentum to be the same. So both objects, the gun and the bullet, have the same magnitude of momentum, the same number of momentum, but they're in opposite directions. One is a plus, one is a minus, so the total momentum is 0, and that's why any gun or any firework will always recoil when this takes place, because it conserves the momentum. So we know the momentum of the bullet will equal the momentum of the gun, so the mass times velocity of the bullet equals the mass times velocity of the gun. So for those to equal the same, so 0 equals mass times velocity of gun minus mass times velocity of bullet, we work it through, they've got to be the same, so when the mass increases, the velocity decreases, and vice versa. So remember, one's a plus, one's a minus, because they're moving in opposite directions. So in a collision or explosion, the larger the mass, the lower the velocity, and we observe this in all guns. So what have we learnt in today's lesson? In a closed system, the total momentum before an event is equal to the total momentum after the event. We call this idea the conservation of momentum. Now, you should be able to use the concept of momentum to describe and explain examples of momentum in an event such as a collision, and you should be able to complete calculations involving an event such as the collision of two objects. So if we're being successful and we've learned in today's lesson, we can calculate the momentum of one object, understand how momentum can be conserved in the system, and then manipulate the conservation of momentum to calculate values. I hope you've enjoyed this lesson, looking at the conservation of momentum in collisions, in explosions, and looking at the concept of recoil when guns are fired. I hope you've had a lovely time learning this, and have a lovely day.